Very good afternoon and warm welcome to this live session. I'm Dr. Vaibhav Pandit, and today for the subject image processing, we are going to topic that is titled JPEG. So this is the topic from the chapter. Basically, the title of the chapter, it is there, image compression here. And if you see the letters JPEG, it is one of the image compression standards here. And now there are two types of the compression here we carry out to save the memory and also to get benefited while we carry out the communication of such information with minimum required things here. So this is one of the lossy type of the compression. As you see, JPEG is just the abbreviation. It basically stands for the Joint Photographic Experts Group here. So we have several of the versions for the JPEG, and most of the times we are very well familiar while working into the digital images here. Now let us have first of all a practice of the problem that will cover all of the necessary steps to understand what exactly the JPEG type of image compression is there, and thereupon, if the time permits, we shall also have the details of the complete JPEG here. So I just start with the problem statement here. So here we have the problem statement starting as perform the compression and reconstruction of the 8x8 input image. Here the image is provided to us in the problem and it is denoted f of m comma n, and the statement continues with the JPEG baseline standard. So in this particular statement, the thing is cleared. We have been asked to perform both the things we have to do. We have to compress the given image sample. The given image sample is of the order 8x8. It means we have the total 8 rows like this and 8 columns. So 8x8, total 64 pixels here we are having as represented f of m comma n. So m and n are simply the representations of how many number of rows and columns here we are having. These are basically the parameters to denote these spatial coordinates, and both m and n are having the value 8 in this. And the compression as well as reconstruction of whatever the compressed result we obtain in the first task, we have to also show, and we have to follow for this particular procedure the JPEG baseline standard. Now the problem statement is not completed. It is also having one supported information. The supported information is of the quantization matrix as provided, again of the order 8x8 here. So here the quantization matrix is denoted by the letter small q. Here we again have 8 rows like this and 8 columns here. So the total 64 elements here we have in the matrix of the order 8x8. So the thing is very simple. We are provided the input image to be compressed, and its corresponding compressed result what we obtain, we need to get that reconstructed to most possibly the original form that we have seen on the previous slide here, and we have to follow the JPEG baseline standard. So let us have the solution for this. So to determine both the things here, the compressed form and the reconstructed form, we will follow the step-by-step approach, and here we shall be applying it. So very first of all, the step to follow, first of all we shall be going for the image compression by JPEG here. The step number 1 is called as level shifting here. So in this level shifting step, what we need to do, we have the 64 elements ordered in 8 rows and 8 columns as denoted by f of m comma n. So from each of this particular element, total 64 elements here, we have to subtract 128 value from that one, and whatever the results we shall be obtaining here, these results we have to again arrange in 8 rows and 8 columns at the respective same places we have to say here. So the level shifted image, see the input image we have denoted by f of m comma n as per the given problem statement. The level shifted image is different from this after the subtraction of 128 value from each pixel value I can say here. So this new image can be denoted with the symbol g of m comma n here. So here the simple relation with the input image and the level shifted image here we show. G of mn is the level shifted image that has been obtained by subtracting 128 as a value from the input image to be compressed, and that it is denoted f of m comma n here. So here we shall substitute f of m comma n in this relation and we'll try to obtain g of m comma n. So as 128 is to be subtracted from each and every place here, we again put a matrix of 8 by 8 order, 8 rows and 8 columns, and each element is having 128 as a value. So here we try to obtain g of m comma n here by this particular subtraction in the matrices here. So here this is the given input image sample as denoted f of m comma n here. So here we are having 183 as the first element, first row, first column. In this first row, the second element is 160, then 94, 153, 194, 163, 132, 165, and so on like this here. Now we have to subtract from every value by 128 like this. So in the second matrix you see everywhere there it is 128 only, and from all these values whatever you take out of these 64 values we have to make a subtraction here. So when you have the subtraction of each and every element at these 64 places here, we get the resultant level shifted image as denoted g of m comma n, and here we arrange the resultant values after we have the subtraction. The differences have been found, and in the first row we have the values correspondingly 55, 32, minus 34, 25, 66, 35, 4, 37. Then in the second row we have 55, 25, minus 12, 48, 59, 38, 2, 41. So this way we have the arrangement of the 8 rows and 8 columns to be the level shifted image as denoted g of m comma n here. Now the next thing is there to perform the step number 2 here. See, the step number 2 is very important. The first step that it was very much simplest, every element has to be perform a subtraction. From the given value we have to subtract 128 here. Now in the step number 2 we have to take the help of two-dimensional discrete cosine transformation here. Now you see here the abbreviation for two-dimensional discrete cosine transformation is 2D DCT here. See, this 2D two-dimensional This is with respect to the type of the signal representation here, or the original form of the signal here. So we generally have the one dimensional signal that we can plot in this particular graphical plane here. So whatever the amplitude value will be there, we can have a plot of it on the vertical axis, and the independent value, the single dimension, if it is 1D, we can have that independent quantity plotted on this horizontal axis here. But image is our two-dimensional signal here. We have the two dimensions like this. So as we have the number of rows from top to bottom and number of columns from left hand side to right hand side here. So in the image plane we have the different kind of the information plotted on both the dimensions simultaneously, hence the two-dimensional form. Now in my previous lectures, those are available on the online platform. I have already taught DCT. So I hope you are very well familiar with the transformation tools as like the Z transform, the Laplace transform, or the Fourier transform. So this is also one of the similar kind of the transformation tool, and DCT stands for discrete cosine transform. As you know, DFT from the family of the Fourier transformation, D stands for the discrete. Here it is again the discrete representation instead of the Fourier transformation. Here it is the cosine transformation. You can check those videos for the more details here. Now the 2D discrete cosine transformation is to be computed for the image that we have obtained as a result of the earlier step. In the earlier step we have level shifted the input image here, and we have denoted the new image as the G of n here. Now you see the G of m comma n is the 8 by 8 order matrix here. In the matrix form we have the representation here. So here for the computation of the discrete cosine transformation, we require the DCT matrix of the same order here. Now when we make the use of that particular 2D DCT of the order 8 by 8 and we operate on this time the input image, it will be G of m comma n. The output image in the discrete cosine transformation domain we shall be denoting as capital G of k comma l here. So let us have one substage where we have DCT matrix of the order 8, and that is given here and represented by the letter small h here. Now you see the small h, again we have 8 rows like this and the 8 columns here. So the values that you see in this particular matrix form as represented by H, these are the coefficient values of the DCT matrix. So as we have this DCT matrix for the order 8 here, we can also have the DCT matrix for the order 2 by 2 or 4 by 4, 16 by 16. So this way we can have the different DCT matrix, and for a fixed order as this is right now 8 by 8 here, it will be the same DCT matrix here. So whatever the image sample it is provided to you other than the one that I have considered in this problem statement, if the order matches, if that particular image sample is again of the order 8 by 8, so the same H matrix you can make the use of for computation of the DCT coefficients here as the intermediate stage to have the image compression by using the JPEG baseline standard here. So you see in the first row we have the coefficient values 0.3536. So this is again repeated for the second stage, third, fourth, fifth, sixth, 7 and 8 here. So in the first row we have all the elements with the same value. The coefficient value is 0.3536 here. Then you check the first column. The first entry we have already talked about. The second entry is of 0.4904, the third one 0.4619, 0.4157, then 0.3536, 0.2778, 0.1913 and 0.0975. Now you see, if you check more details of the DCT matrices of the various orders, you will come to see that the first row and first column element values are always positive for the order as shown here. Now in between we have few of the intermediate values where we have in the negation as well, as I check 0.1913 negative minus 0.4904 here. So this is what the very important matrix that we are going to make the use of. Now there may be a question to your mind, how to remember this much of particular matrix here. See, as far as the examinations are concerned, the problems onto the JPEG compression and reconstruction, if it will be there, so mostly the order of the image sample will be the shortest possible here, so that the DCT matrix will also be for matching purpose of the same order, and it will be quite easy for you to remember those particular coefficient values here. Otherwise, when the practical examination is there, if you are making the use of the softwares as like the MATLAB, thereupon you can have the use of the MATLAB syntaxes for the DCT matrix, and it will directly generate this particular coefficient matrix that we have called it to be the DCT matrix for the given order. Only in that syntax we have to provide the order value, it will generate the corresponding matrix here, and that particular matrix we can operate onto the input image here and will require to obtain the required results here. Otherwise there are direct syntaxes also, so with the help of which if we provide the input image symbol or the variable that has holded that information, that will directly generate the result. You will not be watching or you will not be associated with the element wise values of the matrix that is internally utilized for this particular task here. So now this is the H here. Now how to compute the two-dimensional discrete cosine transformation of the given image here. Now the given image we have level shifted and now it has been denoted g of m comma n. So let us operate g of m comma n with the help of the H matrix. So determination of the two-dimensional discrete cosine transform for the image, here we represent as the domain gets switched from the original to that of the cosine domain here, discrete cosine domain here. We use the capital letters to show the change of the domain here. Here we shall show the image information that is transformed to the new domain by capital G of k comma L instead of small g of m comma n here. Now how to obtain this transformation? See, the input image to be transformed by this mathematical tool discrete cosine transformation with the input image, this particular matrix H is to be multiplied and the same multiplication is again multiplied to the transposed form of the H matrix here. So transposed form of the H matrix is just swapping the rows and the columns here. So whatever the entries we have in the first row, those will be for the first column here. So similarly, if we have a swapping here from the matrix H, we can obtain the H transpose matrix, and if we have obtained the product of these three elements, of course the matrices here, so that time this is nothing but the representation of the information after transformation by the two-dimensional discrete cosine transform tool here. So for the input image that is label shifted and represented g of m comma n and the H matrix as shown previously, we carry out this particular computation and we obtained it to as capital G of k comma L, and here again the resultant is of the 8 by 8 value. So here we have the matrix value with the resultant coefficients into the DCT domain. So the first value we have 312.375 here. Next to that we have 56.2483. Then we have minus 26.5839. Next to that 16.5266, 79.1250. Then we have here minus 60.1429, 26.3002, minus 26.0891. So these are the values of the first row. Now in the first column, after this 312.375 we have obtained minus 37.7090, then minus 19.7657, minus 11.2133, minus 5.6250, then 2.6574, 2.9016 and 3.2668 here. So this way we have operated the label shifted image as denoted G of m comma n with the help of the DCT matrix and its transposed form, and we have obtained the representation of the image in the discrete cosine transform domain here. Now whatever the result we have obtained, you see here the maximum place after the decimal is up to 4 values here. Now we have to round up the values here. So after rounding up the values as represented in the 8 by 8 order here, the value of the two-dimensional discrete cosine transformation is again written for the same notation. The notation is capital G of k comma L here. So you see here 312.375 value has been rounded up to the value 312. So this way in the first row we have the second value 56, then minus 27, 17, 79, minus 60, 26, minus 26 like this. Then in the first column after 312 we have minus 38, minus 20, minus 11, minus 6, 3, 3 and 3, and rest of the all values are also denoted. So we have 8 by 8, the total 64 representations here we have in this particular matrix form, and as represented capital G of k comma L here. So now after this rounding up of the discrete cosine transform coefficient representation here, we have to go for the next step here. The next step is to have the quantization of whatever we have obtained here as the DCT matrix we can see here. So performing quantization of the DCT matrix here. Now recall back the problem statement. In the problem statement we had been provided the quantization matrix of the same order along with the input image sample to be compressed, and further its corresponding result is also of course to be reconstructed back here. So that particular quantization matrix we shall be making the use of for performing this quantization step here. That quantization matrix was denoted by this letter small q, and the quantization for the DCT matrix as obtained in the previous step will be a simple one. We have to make G of k comma L divided by the q here. So here in this particular relationship you see the result of the quantization of the DCT matrix will be denoted by the letter capital Q. Of course it will be into a matrix form here. So whatever the outcome of the earlier step we have, that is computation of the discrete cosine transform coefficients as denoted in the matrix form by capital G of k comma L, it will be divided by the quantization matrix from the problem statement. So from the problem statement we have to take this particular matrix small q and we have to put it into the denominator, whereas the result of the previous step has to be put into the numerator here. So this computation after the substitution of the corresponding matrices of the order 8 by 8 will be looking like this. So capital Q will be equal to the numerator matrix. Here we shall substitute the first row elements are 312, 56, minus 27, 17, 79, minus 60, 26, minus 26. The first column elements are 38 in negation, minus 20, minus 11, minus 6, 3, 3, 3. and now this is divided by the quantization matrix from the problem statement. So we have the first row element for the quantization matrix as 16, 11, 10, 16, 24, 40, 51, 61. Then the first column elements are after 16 we have 12, then 14, 14, 18, 24, 49, 72. Rest of all the elements are also there as provided in the problem statement here. Now you see here, whenever we are working with the matrices here, and especially it is quite convenient to work upon the matrix operation by taking the help of MATLAB environment or the Scilab environment or the equivalent softwares here. Thereupon you see for the multiplication and that of the division here, there are the two types here. One is the direct division of the matrices or the direct multiplication of the matrices, and the another way is to go for element wise here. So whatever the number of row and number of column is there to locate a particular pixel value into the matrix form representation of the image sample, though at the intermediate stage, the same location we have to trace into the another operand with which we are going to have the operation performed here, and that is supposed to be the element wise operation here. So here it is a direct division here, and here we have been obtaining the capital Q again of the order 8 by 8, and here we have the first row elements as 20.1926, then the second element minus 31.2172, 43.7535, minus 18.2401, minus 32.0710, minus 65.2438, then 138.4763, minus 64.3871. This way we have also the first column elements 2.7441, 2.1067, 1.4313, then minus 0.1562, minus 0.4282, minus 0.6655, and then minus 0.2433 here. Then after getting this particular result of the quantization stage here, we have to again round up the values in the matrix form, as again you see after the decimal the 4 place up to 4 place we have the representation. So after rounding up the operation here, the quantized value possibly get to this particular form, the order will be of the same 8 by 8 here. So the first row it will be 25 minus 3 1 3 minus 2 1 0. The second row it will be minus 3 minus 2 1 2 1 0 0 0. The third row it will be minus 1 minus 1 1 1 1 0 0 0. Then to next row, fourth row, we have minus 1 0 0 1 0 0 0 0, and rest of the 4 rows are left with all the element values to be equal to 0 here. Now in this particular representation, the next thing we have to perform the zigzag scanning operation here. So in the zigzag scanning operation, what we need to do here, after the value 20 we have to go for in the same row to the next value, so that it is equal to 5 here. From the 5 we have to go back to the second row, basically the first column here, so it will be minus 3 here. After this minus 3 we have to go into the same column to the next value, that it is equal to minus 1 here, and from this minus 1 we have to go back to the previous row with the second element as minus 2. Then same thing is to be done for the previous row, the next element that has not been recorded, that is minus 3 here. After this minus 3 we don't have any previous row here, so that time we shall go for the next element into the same row, so that it will be 1. So after this one we have to go to the next row and the element that has not been recorded. So after this one we have this minus 1, then we have this again minus 1. So after this minus 1 we have 0, then from this 0 we have this 0, then this 1, this 2, and this 3, then from this 3 we have to go for -2, then from -2 we have to go for 1, then again 1, then 0. So this way the scanning we have to do in the zigzag fashion here. So this is what the way. Now this is the step that I am going to represent as the step number 4 here. You see zigzag scanning of the quantized coefficients as shown in the previous slide here. Now the output of this zigzag scanning we have to collect here, and this has been collected in a sequence. So in the one row matrix form here we shall be representing this particular set of values here. So the first value, as we discussed, that it is 20, then we have 5, then -3, -1, -2, -3, we have 1, again 1, we have -1, -1, 0, 0, 1, 2, 3, -2, 1, 1, then we have 0, 0, 0, 0, 0, 0 6 times, then 1, 1, 0, 1, and EOB. So EOB is the representation of end of the block here. So whatever the values we have recorded here, this is what the end of this particular block here. Now after this particular type of the scanning here in this exact fashion here, we have to collect the DC coefficients and the AC coefficients from this particular set here. So the DC coefficient is the DPCM coded, whereas the AC coefficient are mapped to the run level pairs here. Here whatever the run level is there, this is also one of the kind of the coding here. DPCM is also one of the coding type here. So this way the JPEG baseline standard image compression steps are there here. Now we shall see the decoding part here. So in continuation to the number of the steps, it will be step number 5 here. In the step number 5 we have to have multiplication of the received values with the quantization matrix here. So again there it is the use of the same quantization matrix that it was provided in the problem statement. So after the multiplication with the values that we have received in the earlier slide here in the matrix form, so that we have to do by element wise multiplication here. So on the previous slide in the matrix form 8 by 8 we have the representation by capital Q after rounding stage, and then small q is provided in the problem statement here. So when we have dot multiplication, see in mostly the softwares like MATLAB here, the multiplication of the two matrices are shown with the help of the asterisk sign here. So this is the asterisk sign, and when in between the two variables holding the information of the operands here, there it is a dot asterisk here. So dot asterisk, it means it is the element wise multiplication here. If it would be a division also, if there it is dot slash here, it will be the element wise division here. So whenever dot is provided before the notation of the operation, the syntax, so that time it is element wise operation here. So we just have to substitute the capital Q matrix from the previous slide and the small q matrix from the problem statement here. So we shall be obtaining capital R here. So this is the next stage here. So in the next stage we have for the capital Q, we have 25 minus 3 1 3 minus 2 1 0, and in the first column after 20 we have minus 3 minus 1, then the rest of the 4 zeros, and rest of all other element values are also there. The same substitution we have made here. The small q we have taken from the problem statement. The first two element 16 11 10 16 24 40 51 61, and the first column elements after 16 we have 12 14 14 18 24 49 72 here. So this element wise multiplication will give us the resultant matrix denoted by capital R, the result of this step 5 also. This is equal to again of the order 8 by 8 here. The first row first column element is having the value 320. The second element in the first row, it is holding the value 55. Then minus 30, we have 16, 72, minus 80, 51 and 0 to follow these particular values. In the first column after 320 we have minus 36, minus 14, minus 14, then we have 4 times zeros here. In the similar way we have the element wise multiplication and we have obtained the corresponding values at these many stages here. So the total 64 values after the element wise multiplication here we have obtained here. So this is what the coded form here. Now step number 6 we will have. In the step number 6 we shall be making the use of inverse transformation so that we can have the reconstruction of the values, and we shall try to have its best match to that of the original image sample that it was provided in the problem statement here. So whatever the matrix are here we have, this is what the outcome of the image compression following the JPEG baseline structure. Earlier also we have shown you the values in a set after the zigzag scanning here. These values are most important and this will be utilized for saving in minimal memory here, and it is of course of the lossy type here, the JPEG standard here. So as we are going to have the reconstruction of the image sample that it was processed for the JPEG compression, it is practically not always possible to get the same value, but it is nearby the same here. So let us have that particular step. Now the step number I shall continue in the same sequence. So let us have the step number 6 here. So for reconstruction purpose, as we are required to make the use of inverse transformation, the transformation mathematical transformation tool that it was utilized for compression was a DCT, discrete cosine transform, and that of course as the type of the signal is two dimensional, it is 2D DCT here. So we require for reconstruction the inverse form. So we shall be requiring IDCT. IDCT will stand for the inverse discrete cosine transform here. IDCT, inverse discrete cosine transform. So for inverse discrete cosine transformation, we will put capital R, the result from the previous step of the compression here, to be the input here from the previous step here. So the simple formulation after the computation of the inverse discrete cosine transform, whatever the information we get, let us denote it by capital R1 here. So the simple thing is, perform the inverse discrete cosine transformation of capital R and obtain R1. R1 is equal to IDCT of the matrix capital R here. So when we perform the IDCT of R here, so here also for performing the inverse discrete cosine transformation, for the inverse transformation also the corresponding IDCT matrices of the same order are also available here. So for the order of 8 by 8, we can use the similar kind of the matrix that we had for the forward transformation denoted by small h here. So utilizing it and working it onto the capital R, we obtain capital R1, and this is again in the 8 by 8 order form here. These are the respective values after this particular computation. We have 67.2735, the first row first column element, then 11.6804, minus 8.5522, 19.5462, 69.0910, then 42.5608, minus 8.1956, 41.9083 here. Now after this we have the first column next values here. After 67.2735 we have 57.6440, then 46.1672, 40.9613, 43.5517, 49.2704, 53.2433, then 54.5383. So in the similar fashion we have rest of the number of rows and columns if you go. So the total 64 values we shall obtain here after this particular operation here. Now this is just the application of the inverse discrete cosine transformation, and you see after the decimal point up to the 4 places we have the representation of the resultant form here. Now we have to again carry out the rounding. So after rounding, the capital R1 will be the same notation for the result here, and R1 will be given as, in the first two we have 67, 12, minus 9, 20, 69, 43, minus 8, 42. In the first column after 67 we have 58, 46, 41, 44, 49, 53 and 55 here. So this way rest of the values, total 64 values we have in this matrix representation here. Now after having the round up of these particular values and again represented for the same variable capital R1, we have to go for performing the next step, and the next step in the sequence it will be step number 7. So in this step number 7, if you recall back whatever the processes we have done in the carrying out of the compression process, before the forward discrete cosine transformation on the two-dimensional signal, we have been making the use of level shifting with the value 128 subtracted from each element value here. The same here we have to reverse. So here we shall be performing again the level shifting operation to the original level. We shall try to rearrange the values. So here the 128 values that it was subtracted in the forward transformation for achieving the compression, for reconstruction purpose 128 is to be added for each and every value that is representing the pixel intensity for the particular location. And this time whatever the R1 here we have, so we shall add with the 128 and will require to obtain the capital R as the reconstructed image here. So let us have capital R is equal to R1 plus 128. So R1 is of the order 8 by 8. So we create one matrix of again the same order 8 by 8 with all the values, 64 values, with the same 128 as the value here. So we just have the substitution like this. So this is what the matrix we have obtained from the previous step, that is for the capital R1, and this is what the matrix we have generated for the second term in this particular relation here. So every entity we have to add 128. 67 will be added by 128, 12 will be added by 128, minus 9 will be added by 128, 20 will be added by 128, 69 will also be added by 128, 43 will also be added, then minus 8 is to be added by 128 and 42 also to be added by 128. So this way I have shown you the operation into the first row only. The same thing we have to carry out on all these particular next rows, total 8 rows here we are having, and the resultant matrix will be denoted by the capital R here. So here we obtain the capital R values. In the first row you see the values are 195, 140, 119, 148, 197, 171, 120, 170. In the second row we have 186, 153, 143, 158, 193, then 168, 124, 175, like this. So these are the next row values obtained from the same procedure as we have discussed here. Now this is what the reconstructed image here. So let us compare this reconstructed image with the original image that it was provided in the problem statement, and it was denoted f of small m comma small n here. So here we have obtained the image that it was provided in the problem statement. If you compare The first row, first column matrix value we have obtained in the reconstruction to be 195, whereas in the original form it was 182. Now instead of 160 we have obtained 140 as the value. Instead of 94 we have the value 119. Instead of 153 we have obtained 148 if you check back the previous slide. Instead of 197 we have obtained 100 and instead of 194 we have obtained 197. Instead of 163 we have obtained 171. Instead of 132 we have obtained 120, and instead of 165 we have obtained 170. So here it was. This is the reconstructed image as denoted by capital R, and this is the image as provided to be compressed and further reconstructed back. Both the processes to be done following the JPEG baseline standard image compression technique here. So this is what the completion of the problem statement that it was associated to. I hope the procedure is quite very much clear to you people. The first step is very simplest, that is to perform the level shifting operation. After level shifting we have to make the use of the transformation matrix here. The kernel matrix, it is also one of the name for the same. So whatever the order of the input image is there, of the same order size we have to select that particular H matrix for the computation of the discrete cosine transform coefficients, and then we have to carry out that transformation, and then further the quantization step will be carried out. Along with we have to also round up the values. The quantization procedure is carried out as per the quantization matrix as already provided in the problem statement, so that it is the compression process, and by the zigzag fashion we have to record the numbers also, and the reversal is just to reconstruct back the image here. So as this is the lossy type of the image compression standard, we have not obtained the exact same values as it was provided in the original image sample here, but nearest to that one, whatever the trend we have, whether as we shift from one pixel to another pixel, whether the intensity values or the pixel values are increasing or decreasing, the same trend we have seen while we have reconstructed back. So this was the problem associated to the JPEG that is standing for the Joint Photographic Experts Group here. So this is one of the best lossy compression technique, very popular here. Now as we have time here, I will like to discuss few of the details behind this particular JPEG. If you see the image compression as a specific chapter here, you will find that there are several of the image compression standards here, and the basic categorization or the classification of the image compression standards will be into the three parts here. The first part will be binary image compression standards. The second part, it will be the continuous tone still image compression standards, and the third part will be the video compression standards here. So out of these three particular categories, our JPEG image compression standard is belonging to the second one, that is the continuous tone still image compression standards here. So let us have few of the details with respect to the continuous tone still image compression standards, and if the time permits, after the completion of the details of this particular standard, especially the JPEG, I'm not focusing on the JPEG 2000 here, it has a small modification from the earlier one here. We can also solve one of the example here. So the information regarding the continuous tone still image compression standard is like that. The CCITT and the ISO have defined several continuous tone image compression standards here. So what is this CCITT and ISO here? So ISO, I hope you are well familiar with. The ISO stands for the International Organization for Standardization here, and CCITT, I hope it is new to you people. This is basically the abbreviation with the full form in the French language here. If you have this in English, it is basically the International Telegraph and Telephone Consultative Committee here, but the abbreviation is the same, that is used CCITT here. So these are the two agencies. They are governing the rules related to this particular domain here. They have defined several of the continuous tone image compression standards here, and these standards, various pages we have here for the adoption process here, they address both the monochrome image as well as the color image here for compression purpose here. So I hope a better clarification you have regarding the monochrome image and the color image here. In the monochrome image, mono means single, chrome means the color here, or the as you compare it on the frequency range here on the electromagnetic frequency spectrum diagram here. So a single frequency range here we are using, that is why in the visualization we have a same kind of the color here. So basically the binary image or the grayscale image, so they are belonging to this particular category. And when you have a differentiation with respect to multiple frequency bands, as like the red, green, blue, near infrared, and the nearby bands to this R, G and B here, so it will be a colorful image, basically a multispectral image here. For the color image, basically we are having only the three bands R, G and B only. So we have a simple categorization of the images. First of all, to be the binary image, that is only having the two shades, either complete white or a complete black here. Then we have shifted to the grayscale image. So we have the complete white and complete black, but along with we have the different shades in between the white and the black here. So that is grayscale image. Then the color image in terms of the R, G and B, red, green and blue, and then the multispectral, hyperspectral images are of course there here. So this is the continuous tone still image compression standards. I have already discussed that there are basically the three categorizations made for the image compression standard. The first one is the binary image compression standard here. So in contrast to the earlier image compression standard, the binary here, this continuous tone standard is basically having the principal focus on the lossy transformation coding technique. And as just now we have completed one of the example for practice purpose for the JPEG compression and then the reconstruction here. This is belonging to this particular second category. So that is continuous tone still image compression standard here. The example here we have, that is the original DCT based JPEG standard. So whatever the problem we have practiced here, that is belonging to this particular example. Here we are having the use of the original discrete cosine transformation matrix for computation of the corresponding coefficients, and the rest of the process you know better, and that is for the JPEG standard here. Next to that, instead of having the discrete cosine transformation, as this is one of the popular mathematical transformation tool here, there are also several options other than the discrete cosine transformation. For example, the wavelet theory is also gaining much information and popularity because of its precise results here. So wavelet based JPEG is also there. That version is named by JPEG 2000 standard here, and next to that also we have the JPEG LS standard. So these are the several of the examples that come to this particular category, what we have titled as continuous tone still image compression standards here. Now focusing more attention onto just the JPEG, I will just highlight few of the important points here. Yes, so the JPEG is the standard, one of the most popular and the comprehensive continuous tone still frame compression standards here, and it is defining the three different coding systems here. So one by one we shall have few of the summary points related to these ones. The first category of the coding system is a lossy baseline coding system here, and this lossy baseline coding system is based on DCT. DCT standing for the discrete cosine transform, we have discussed it a lot, and this is adequate for the most compression applications here, hence it is very much popular as well. The second one is an extended coding system. So it is for the greater compression, achieving more and more compression with minimal number of bits. We have to try for saving that much of image information here, and also achieving the higher precision. So the precision in terms of, while we have the reconstruction of the original image sample, it is not matching the things because it is of the lossy type here. So we will try to have a match, best match to the original value, so a higher precision in the technique here, or a progressive reconstruction application. And the third one, a lossless independent coding system, and this is for the reversible compression only here. So this is what the three different coding systems for the JPEG here. Now, what is the thing for the compression to be with the JPEG compatible here? So to be JPEG compatible, a product or a system must include the support for the baseline system here, and there is no particular file format, the spatial resolution or the color space model defined or specified for the JPEG here. And in the baseline system, which is often also known by the name the sequential baseline system, the input and output data precision is limited to only 8 bits, whereas the quantized DCT values are restricted to 11 bits. The compression itself is performed in the three sequential steps. These steps we have seen already. The one, DCT computation, the second one, simply quantization, and the third one is variable length code assignment here. In the previous live session for the same subject, image processing, I have addressed image compression model. Thereupon I have taken a practice of the coding. So variable length coding, I hope you have the idea, or you can attend my previous lectures so that you get the complete details of the same here. Now the image is here first of all subdivided into the pixel blocks of the size 8 by 8, which are processed left to right and top to bottom. And as 8 by 8 block or sub image is encountered, its 64 pixels are level shifted by subtracting the quantity 2 to the power n minus 1, where 2 to the power n is the maximum number of gray levels. So the problem that we have solved, we had been already provided the order of that image sample to be of the 8 by 8, so total 64. So we have not required to follow the first point here, that the image to be first of all subdivided into the pixel box of size 8 by 8 here. We have directly applied the thing from the second point here. Next to that, the two-dimensional discrete cosine transformation of the block, that means the entire image sample as provided in the problem statement by f of m comma n, we have been operated here, and the computation of the two-dimensional discrete cosine transformation was done. Further, it was also quantized and reordered using the zigzag pattern as we have done here. Here it is one more illustration to show it for the form of one-dimensional sequence of the quantized coefficients here. So here it is what the illustration having the example having the four parts. So we have a typical in the first part, the zonal mask, then the zonal bit allocation, then the threshold mask, and the thresholded coefficient ordering sequence here. So you just have the attention to the fourth one, thresholded coefficient ordering sequence here. So right from 0 we have to go for 1, then 2, then 3, 4, 5, 6, 7, 8, 9, then 10, 11, 12, 13, 14, then 15, 16, 17, 18, 19, 20, then 21, 22, 23, 24, 25, 26, 27, then 28, 29, 30, 32, 33, 34, 35, then 36, 37, 38, 39, 40, 41, 42. Then you see we have 43, 44, 45, 46, 47, 48, then 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, and 63. We had started with the designation as 0, that is why we have ended at 63. Total 64 entries are there here. So total 64 entries here we have. Now The next thing here we have, since the one dimensionally reorder array, as we have shown in this particular four parts here, especially the figure D here, so it is qualitatively arranged according to the increasing spatial frequency. The JPEG coding procedure is designed to take the advantage of the long runs of the zeros that normally result from the reordering here, and in particular the non-zero AC coefficients are coded with using a variable length code that defines the coefficient's value and the number of preceding zeros here. The DC coefficient is difference coded relative to the DC coefficient of the previous sub-image. The tables provide the default JPG Huffman codes for the luminance imagery here. So here we have the tables. So a table for JPG coefficient coding categories here. So on the left hand side we have the first column, the range. The range you can see for the first entry we have 0, then -1 to -1, then -3 to 3, -7 to 7, -15 to 15, -31 to 31, -63 to 63. So this is all 2 to the power something here. Okay, then the DC difference category, here we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After 9 we have capital A, B, C, D, E, F, and the AC category for the first entry it is not applicable, and then we have again 1, 2, 3, 4, 5, 6, 7, 8, 9, capital A, B, C, D, E, and then not applicable here. After that we have the JPG default DC code here for the luminance case. So this is what the table, the categories here we have in the first column 0, 1, 2, 3, 4 and 5. The base codes for the 0 it is 0, 1, 0, for the 1 it is 0, 1, 1, for the 2 it is 1, 0, 0, for the 3 it is 0, 0, for 4 we have 1, 0, 1, then for 5 we have 1, 1, 0. The lengths here we have 3, 4, 5, 5, 7, 8. The categories 6, 7, 8, 9, capital A, capital B, the corresponding block code and the length here. Now the JPG default AC code for the luminance code, here we have the first column run oblique, the category type here we have first of all the first entry run, and in the oblique after oblique we have the category, the base code, length, run category, the base code, length here. So this table is continued to the next entries. So here we have this particular table. So lot many entries here we have in this particular tabulation. So here for the luminance, here we have the consideration. So the JPG basically recommends the luminance quantization array that can be scaled to provide a variety of the compression levels. And although the default coding tables and the proven quantization arrays are provided for both the luminance and the chrominance processing, the user is free to construct the custom tables and for arrays which may in fact be adapted to the characteristics of the image being compressed here. So this is the very important feature of the JPG image compression standard, which brings the flexibility to certain extent for the user to have the image compression here. So this was all about the details of the JPG here. I have few more examples also to work out on the JPG, but as we have a time limitation, I just stop here. And if you want certain more information, you can attend my lectures that are already available on the Ekeeda platform. And by the next week we shall meet with another topic in the subject image processing here. Basically in this image processing, this was our 14th lecture, and up till now we have considered various topics for the fundamental image processing steps here. The image processing steps, after the image acquisition we have the image enhancement into the spatial domain, into the frequency domain also, then image restoration also we have done, the color image processing we have also seen. We have also studied the wavelet theory along with the multi-resolution analysis, and then from the last lecture we have started with the image compression. So the two topics I have addressed for the image compression. The next thing I will focus on the fundamentals of the morphology operations. So do attend the next lecture. Thank you.